Hello, hello, everybody. You can actually see me. I know you probably don't want to, but you can. I am broadcasting from the dungeon that is my basement. We're going to try this on Zoom today instead of what I've been using. We'll see how it goes. First, let's get rid of my face so you don't have to look at it anymore. Okay, you just got done taking that quote quiz on single-step experiments and mutually exclusive events. Today, we're dealing with multi-step experiments, which basically means flipping a coin a bunch of times and rolling a die, or rolling multiple dice, or more realistically than drawing one card, drawing multiple cards. Basically, the fundamental counting principle applies here. What's the fundamental counting principle? When you have multiple things going on, how do you find the probability of all of them occurring? You multiply. That's it. This is called multi-step experiments, but it's called the multiplication rule. And independent events means that things are being done with replacements. We'll explain that later. First, a few visual ways to see these events occurring. One is with a tree diagram. Okay, so let's go to example one. It says flip a coin 3 times. All right, when you flip a coin, period, let me start here with what a tree diagram is. It starts with a singular point. I could either flip heads or tails. This column represents the first toss. Even if I flip heads, though, the second toss can still be heads or tails. Likewise, if I flip tails first, the second toss could be heads or tails again. This second column represents the second toss. There are 4 total options after 2 tosses. Then, after 3 tosses, things expand again. I could go heads, tails, 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 heads, tails. To find the total number of outcomes when you, oh, by the way, this represents the third coin toss, this third column. To find the total number of outcomes, just count down the last column. There are 2, 4, 6, 8 total outcomes when flipping a coin 3 times. What a tree diagram does is it helps you see all the possibilities without having to do any math. For instance, find the probability of 3 tails. Well, if I flip a coin 3 times and get tails, 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 the only branch I see that has tails, tails, tails is that one branch right there. That actually represents one branch, not 3. One branch of 3 coin flips. So that's one branch out of the 8 branches. I'm done with part A. The tree diagram helped me see that answer. 2 heads and 1 tail. Let's find the branches that have 2 H's and 1 T. This branch does H, H, T. That's one branch. How about H, T, H, heads, tails, heads? That's a second branch. How about tails, heads, heads? That is a third branch. There are a total of 3 branches that have 2 heads and a tail out of the 8 total branches. That's the beauty of a tree diagram, seeing the possibilities in front of you. Same thing for a family of 3 children. Now, I realize that in recent years, the number of possibilities have expanded. For this personal example, or this particular example, let's just choose boy or girl. Looks exactly like heads and tails because the options are the same. There are 2 outcomes as far as this question is concerned. What's the probability of having all girls? I see G, G, G right here. So there is the one branch that has all girls, 1 branch out of 8. 2 boys and 1 girl in any order. So once again, I'm going to look for 2 B's and a G. There's 2 B's and a G. Here are 2 B's and a G. And last but not least, here are 2 B's and a G. So that's 3 branches out of 8. The bottom line from this first page is that if you have a tree diagram, you don't have to do math. Pretty nice. And also, if order doesn't matter, it's up to you and you and you to think of all the possible ways to arrange the items in question. In this case, there were 3 possible ways, so 3 ways out of 8. That's what we're going to get to without drawing a tree diagram for the future examples right now. Let's get down to these. I'm not doing all the examples. I'm going to pick a few and go through with them. All right, so roll 2 dice successively. So you're rolling 1 die and then another. So what's the probability of rolling 2 5s? I'm going to do dashes here. So rolling a 5 and then another 5. There's a 1 out of 6 chance of rolling a 5. There's another 1 out of 6 chance of rolling a second 5. That's a 5 and then a 5, so fundamental counting principle. I multiply in between. The good news for this particular part of the probability unit, I don't need you to multiply them or even reduce them. You can leave the answer just like that. Nice. A 3 and a 5 in any order. So let me do dashes here. I could do a 3 and then a 5. So what's the probability of rolling a 3? Well, that's 1 out of 6. 3 is one number out of the 6. Same for 5, 1 out of 6. And I'm going to multiply because it's a 3 and then a 5. But is this the only way to roll a 3 and a 5? No. We could also roll a 5 first and then a 3 second. But here's my question. Are these probabilities of these two options any different? No. They're both 1 out of 6 times 1 out of 6. But because there are two options, two ways to roll a 3 and a 5, I am going to take those fractions and multiply them by the two ways to arrange them. That's how this works. When there is no particular order, you need to think of all the ways that items can be arranged and multiply the fractions by that number. That's it. How about 1, 5? All right, so let me do 2 dashes again. So I could roll a 5, and then I could roll something else besides a 5. Well, there's a 1 out of 6 chance of rolling a 5. But then how many other numbers are there besides 5? 5 other numbers. So there's a 5 out of 6 chance of rolling something else besides that. However, I could also roll something else and then a 5. So I take these probabilities and I multiply them by the two ways that there are to get 1 5 and one number other than a 5. That's it. Pause and repeat any questions you need. So look them over again. 4 is an important one. I'll do 2 more questions. Okay. What's the probability of when I draw 3 cards with replacements? What does that mean? It's very unrealistic, but it means I draw a card, then I take it back before I draw the next card. So there's always 52 cards in my hand. Like I said, unrealistic, but for the purposes of this question, we'll go with it. 3 aces. So let's do this right now. Ace, ace, ace. Ace, ace, ace. Go to your card distribution if you need to. There are 4 aces out of 52 cards, times another 4 aces out of 52 cards, times another 4 aces out of 52 cards. Doesn't matter what ace I draw. Doesn't distinguish that. There's a fundamental counting principle. And I'm done with part A. That's it. A 7, then an 8, then a 9. So the order is very specific. It's got to be 7, then 8, then 9. There are 4 7s in the deck. There are 4 8s in the deck. And there are 4 9s in the deck. But because this is the only order that they can be drawn, 7 first, 8 second, 9 third, I am done with this particular question. That's it. Okay. How about part C? 7, 8, 9 in any order. Do these probabilities change? They don't. So I'm still going to draw 3 dashes, and I'm going to call them 7, 8, 9. So that's still 4 to 52 times 4 to 52 times 4 to 52. However, because the order can be in any way, shape, or form, I need to think of all the ways to arrange 7, 8, 9. And I'm going to do that here. How about 7, 8, 9? 7, 9, 8. How about 8, 7, 9? 8, 9, 7. 9, 7, 8. And 9, 8, 7. There are indeed 6 ways to arrange those 3 numbers. So I need to take these fractions and multiply them by the 6 ways that I can arrange a 7, an 8, and a 9. Let's move on to letter D. Only 2 aces in any order. One of the biggest mistakes that happens in part D is people draw 2 dashes, they go ace, ace, and they go 4 out of 52 times 4 out of 52, and then they have a coffee and a donut. The problem with this is that we are still drawing 3 cards. That's the issue. So I need a 3rd card. So it could be anything other than an ace. How many other cards are there besides aces? Well, there's 48 of them. 52 minus 4. So 48 out of 52. However, it could be in any order. So I have to think of the ways to do this. I can go ace, ace, and something else. Or I could do ace, something else, and ace. Or I could do something else, ace, ace. There are 3 ways that I can see right there to arrange 2 aces and something else. So I need to multiply these fractions by 3. Last but not least, 3 black cards. That's just spades or clubs, and it doesn't distinguish, so it's just a black card, black card, black card. That's half the deck. So 26 out of 52 times 26 out of 52. And then last bleed times 26 out of 52. The question before I move on is, why is part C multiplied by 6 and why is part D only multiplied by 3? It's a question often asked. And can you see the difference? The reason C is multiplied by 6 is because there are 3 distinct items going on here, a 7, an 8, and a 9. 3 distinct things. And there are 6 ways to arrange those 3 distinct items. 3 factorial, if you're really thinking about it, right? 3 times 2 times 1. Why in D do we only multiply by 3? The reason for that is because 2 of the items are the same and only 1 item is different. So there are only 3 ways to manipulate that one item that's different from the rest. All right, let's see if we can get one more question in. Let's go all the way down to number 10. Number 10 says there are 15 marbles. And I'm just cutting to the chase because I'm running low on time. 2 blue and a red. So we got blue, blue, red. How many blues are there? 5. 5 out of 15. Another blue is 5 out of 15. Red is 6 out of 15. Multiply in between, fundamental counting principle. And then think of all the ways I could do blue, blue, and red. I could do blue, blue, red. I could do blue, red, blue. And I could do red, blue, blue. So I'm going to multiply by the 3 ways that I can arrange 2 blues and a red. No yellow. All right, well, there are 4 yellow. That means there's 11 that aren't yellow. So that's 11 out of 15 times 11 out of 15 times 11 out of 15, and I'm done with part B. 1 of each color. So that's a blue, a red, and a yellow. There are 5 blue out of 15, 6 red out of 15, and 4 yellow out of 15. But because these are 3 distinct objects, it doesn't say they have to be in that order, so I'm going to multiply by the 6 ways. Yes, if I scroll back up, there are 6 ways to arrange 3 distinct objects. So I multiply by those 6 ways. I hope this has helped, and let me know if you have any questions.